Welcome back. This is part 2 of a video lecture on section 4.4, Similarity and Diagonalization. Now in part 1, we covered an illustrative example and similar matrices. In this video lecture, we pick up where we left off with the topic of diagonalization. Now let's begin by discussing what it means to say that a matrix is diagonalizable. An n by n matrix A is diagonalizable if there is a diagonal matrix D such that A is similar to D. That is, if there is an invertible n by n matrix P such that P inverse times A times P is equal to D. Now, of course, this is equivalent to saying that the matrix A can be represented as the product P times D times P inverse. And this is the way I like to articulate diagonalizability. The matrix A is diagonalizable if it can be expressed in the form P times D times P inverse. Now, a matrix that's similar to a diagonal matrix, a matrix that satisfies an equation like this, has a very special property, and we're going to take this up in our next problem. So let D be an n by n diagonal matrix, and let P be an invertible n by n matrix with columns P1 through Pn. Now, I'm going to let the entries along the main diagonal of D, I'm going to label them lambda 1 through lambda n, and we can see here our matrix P is being represented by its columns P1 through Pn. Now, we're going to let A be the matrix P times D times P inverse. For each I, where I ranges from 1 to n, let's show that A times P sub I is equal to lambda sub I times P sub I. In effect, what we're showing is that each and every one of these columns is an eigenvector of the matrix A with corresponding eigenvalues. Now, in addition, we know this matrix P is invertible. And by our fundamental theorem on invertible matrices, we know that these columns, P1 through Pn, must be linearly independent. So, in effect, what we're showing is that this matrix A has n linearly independent eigenvectors. Now, let's go to the document camera and work out the details of the solution to this problem. All right, welcome to the document camera. In this problem, we've got a matrix P whose columns are represented by P1 through Pn. We've got a diagonal matrix D with elements on the main diagonal consisting of lambda 1 through lambda n. We're told that the matrix P is invertible, and we're forming a new matrix called A, which is just the product of P times D times P inverse. Now, our goal in this problem is to show that the ith column of the matrix P is an eigenvector for A with eigenvalue lambda sub I. In other words, P1 is an eigenvector for A with eigenvalue lambda 1. P2 is an eigenvector for A with eigenvalue lambda sub 2, on down to Pn is an eigenvector for A with corresponding eigenvalue lambda sub n. Now, to get started, what we really need to understand is this relationship, and this is very simple. When I take the matrix P and I multiply it by the ith unit direction vector in Rn, we know what that's going to do. That's going to pull out the ith column of the matrix P. So P times the ith unit vector in Rn is going to give me the ith column of P, P sub I. Now, another way to think about this relationship is to multiply both sides by P inverse and realize that E sub I is P inverse times P sub I. Okay? And that ends up being like the key insight into solving this problem. Now, what I want to do is I want to look at what happens when I apply the matrix A to the vector P sub I. Now, A is nothing more than the product of these three matrices, so this is the same thing as P, D, P inverse applied to the vector P sub I. Now, by association, I can think of this as PD times P inverse on PI, but we know that that's just E sub I. And again, by association, I can think of this as P times D times E sub I. But once again, when I take D and multiply it by this ith unit direction vector in Rn, I'm simply going to get the ith column of this diagonal matrix. And that ith column consists of lambda I in position I and zeros everywhere else. And one way to think about that is we can think of this as lambda I times that unit direction vector, E sub I. Now I can pull this scalar through. And once again, I can use the fact that when I apply the matrix P to that unit direction vector, E sub I, I just get P sub I. Okay? So what we're seeing is that each and every column of this matrix P is an eigenvector of the matrix A with corresponding eigenvalues on this main diagonal, the main diagonal of this diagonal matrix D. Now, we want to make one more observation though. We want to make one more observation. Since this matrix P is invertible, we know from our fundamental theorem on invertible matrices that this collection of eigenvectors is linearly independent. So let's also draw that out. Let's pay attention to that fact too. So the collection P1 through Pn, not only are these all eigenvectors for the matrix A, these are linearly independent. And since there are n of them in Rn, this would form a basis for Rn. Okay, so that brings a conclusion to our solution to this problem. Let's head back to the class notes and continue. Now, in order to develop a deeper understanding of the problem that we just worked, let's think about the following situation. Imagine a matrix A being represented as the product of three matrices. This first matrix is an invertible 2 by 2 matrix. The second matrix is a diagonal matrix, and the third matrix is the inverse of the first matrix. So A is of the form P times D times P inverse. Now, according to our work in the solution to the previous problem, we know that the eigenvalues of A sit here on the main diagonal of the matrix D. The eigenvalues of A are -4 and 7. And the eigenvectors are in the columns of this matrix P, namely the vector consisting of 3 and 2 and 4 and 3. So this eigenvector 3, 2 corresponds to an eigenvalue of -4, and this eigenvector 4, 3 corresponds to the eigenvalue of 7. Now our next result, theorem 4.23, gives us necessary and sufficient conditions for a matrix to be diagonalizable. So let A be an n by n matrix. Then A is diagonalizable if and only if A has n linearly independent eigenvectors. Now, when we think about that statement, there's really two different implications that are being asserted. First, it's saying if A is diagonalizable, then A has n linearly independent eigenvectors. And this is essentially what we've already shown in the solution to that problem. What we need to show is the second half, and that says this: if A has n linearly independent eigenvectors, then A can be expressed in the form P times D times P inverse for some invertible matrix P and some diagonal matrix D. So let's go to the document camera and work out part 2, or the second part of theorem 4.23. All right, welcome to the document camera. We're going to try to prove the second part of theorem 4.23, and here's the setup for that part. We're given an n by n matrix, and we're told that this matrix has some pretty special properties. It has n linearly independent eigenvectors. We'll call them P1 through Pn, with corresponding eigenvalues lambda 1 through lambda n. Now, what we want to show is that this matrix is diagonalizable. We have to show that it's similar to a diagonal matrix. Now, what we need to do is come up with candidates for a matrix P, an invertible matrix P, and a diagonal matrix D, and show that A can be written as P times D times P inverse. Now, here are the choices of P and D that are going to work for us. First, I want to let P be the matrix with columns given by these eigenvectors, P1 through Pn. And I want D to be the diagonal matrix that I get by taking these eigenvalues in exactly the corresponding order and putting them on the main diagonal. Now here's a crucial part of the argument. We're going to make strong use of the fact that these columns, well, that the columns of the matrix P, that these vectors are linearly independent. By our fundamental theorem on invertible matrices, if these columns are linearly independent, then this matrix is invertible. So we're going to leverage the fact that these eigenvectors are linearly independent to allow us to assert the existence of an inverse for that matrix P. So this inverse is guaranteed by the linear independence of this set of eigenvectors. Okay, now what we need to do is form the matrix product P times D times P inverse and show that that's equal to the matrix A. Now we don't know that this is equal to A. So what I'm going to do is just temporarily call the product of P, D, and P inverse, I'm going to call that matrix B. Now we have to show that B is equal to A. All right, so that's what this problem has been reduced to. We need to show that this equivalence between these two matrices will force A to be equal to P times D times P inverse. Now here's the crucial observation that we have to make. We have to kind of put two things together in order to get there. The first thing we need to understand is that A and B agree on every one of these eigenvectors, P1 through Pn. Let's see if we understand why that has to be the case. Why do A and B agree on this collection of eigenvectors, P1 through Pn? Well, we know by definition, right? When I apply A to P sub I, I'm going to get lambda I times P sub I. And that comes directly from the fact that these are eigenvectors for the matrix A. On the other hand, we know from our previous work that anytime I have a matrix that's in this diagonal form, we know that the ith column of this matrix P is in fact an eigenvector for this matrix B with an eigenvalue that's correspondingly in the ith row or the ith column of this matrix D. So we also know that B applied to P sub I is also equal to lambda I times P sub I. So what this is telling us is that A at P sub I and B at P sub I are equal. And this is true for every single eigenvector in the list P1 through Pn. Now, let's see how we can use that fact to show that A and B are equal to each other. So let X be any vector in Rn. All right? We know that the vectors P1 through Pn being linearly independent and being n in number form a basis for Rn. So we can write X as a linear combination of the basis vectors P1 through Pn. All right? Now let's apply A to X. A at X, or A times X, is A applied to the linear combination. But A distributes across this vector addition, and I can pull the scalars through. And so this can be rendered as A1 times capital A applied to P1 on down to AN capital A applied to Pn. But we know that A and B agree on all of these eigenvectors. And so we can write this as A1, B applied to P1, all right, so here we're really making strong use of the fact that A and B agree on every one of those eigenvectors P1 through Pn. So we can freely substitute B1 P1 for A1 P1 here on down to ANPN equals BNPN. All right. Now we're going to basically factor the B out on the left and write this as B applied to the linear combination A1P1 on down to ANPN. But once again, that linear combination is just the vector x, and so this is just B times x. So we know that for every single vector in Rn that A times x is equal to B times x. And that means that A and B have exactly the same entries, right? We know that column by column, the matrix A and the matrix B must be the same because A at x and A times x and B times x are equal for every x in Rn. So this brings a conclusion to our proof. We now know that A is equal to B, and that is tantamount to saying that A is representable as P times D times P inverse. A is diagonalizable. All right, let's head back to the class notes and continue. All right, let's work a problem together. Show that the matrix A is diagonalizable. Now, the first thing we would need to do is find the characteristic polynomial of the matrix A. And so the characteristic polynomial of A in the variable lambda is going to be what I get when I take the determinant of A minus lambda times the identity. When we carry out this determinant calculation, we find that the characteristic polynomial of the matrix A is lambda squared minus 2 lambda minus 3, and that can be factored as lambda plus 1 times lambda minus 3. And so we can see that the two roots of this characteristic polynomial, the eigenvalues of the matrix A, are -1 and 3. The spectrum of A consists of -1 and 3. Now, we know that there are eigenvectors that correspond to each of these eigenvalues, so let's let P1 and P2 be the eigenvectors corresponding to lambda equals -1 and lambda equals 3. Now, the eigenvectors P1 and P2 are linearly independent since they correspond to distinct eigenvalues. That's something we looked at back in section 4.3. So we know that P1 and P2 are linearly independent, and that means that A is diagonalizable according to theorem 4.23. Now you'll notice in solving this problem, we actually never found P1 and P2 explicitly. Nonetheless, we know that they exist, and since there are two of them, and since they are linearly independent, we know that the matrix A is diagonalizable. Now, let's think about how we could generalize this. Let's imagine that A were a 3x3 matrix. If A had 3 distinct eigenvalues, then we would have 3 different eigenvectors, one for each eigenvalue, and those 3 eigenvectors would necessarily be linearly independent. And likewise, if A were a 4x4 matrix or a 5x5 matrix, as long as the number of distinct eigenvalues is equal to the number of rows or the number of columns of the matrix, we know that that matrix will be diagonalizable. And this is enshrined in theorem 4.25. This theorem says that if A is an n by n matrix with n distinct eigenvalues, then A is diagonalizable. Now, theorem 4.25 gives us a very simple and clean way of showing that certain matrices are diagonalizable. If, for example, A is a 4x4 matrix, and if A has 4 distinct eigenvalues, then in fact that matrix A is diagonalizable. But what happens if A is a 4x4 matrix and it only has 3 distinct eigenvalues, or 2 distinct eigenvalues, or possibly 1 eigenvalue? What do we do in that case? Theorem 4.25 will not cover that scenario. Now, in these cases where the number of distinct eigenvalues is coming up short of the number of rows or the number of columns of the matrix, in these cases, some extra analysis is required. Now let's look at the following problem. Let's show that the matrix A is diagonalizable. Now when we compute the characteristic polynomial of A, we find that it factors as -1 times lambda plus 1 squared times lambda minus 2. And this shows that A has only 2 distinct eigenvalues, namely -1 and 2. Now, in order to show that A is diagonalizable, I have to show that A has 3 linearly independent eigenvectors. So in order to do that, we're going to have to carry out some further analysis, and this involves computing the eigenspaces associated with each of these eigenvalues. Now, when we examine the eigenspace corresponding to the eigenvalue of -1, we find that it has dimension 2. There are 2 linearly independent vectors that span the eigenspace E sub -1. Likewise, when we look at the eigenspace associated with lambda equals 2, we find that it has dimension 1. It's spanned by this single vector. Now it turns out, since these bases correspond to distinct eigenvalues, that when we lump them together, they will form a complete linearly independent collection. In other words, the totality of these 3 vectors will be linearly independent. And so by examining these eigenspaces, we can find 3 linearly independent eigenvectors for the matrix A. So in fact, A is diagonalizable. Now let's think about why we were successful in showing that this particular matrix A is diagonalizable. Now remember, the difficulty is this. This matrix A has only 2 distinct eigenvalues, namely -1 and 2. And so we cannot make a simple appeal to theorem 4.25 to show us that this matrix is diagonalizable. On the other hand, there's a strong sense in which we can say that this matrix A has 3 eigenvalues when we list them according to multiplicity. Remember that this eigenvalue of -1 is coming from the factor of lambda plus 1 squared, and that means that lambda equals -1 has an algebraic multiplicity of 2. And this eigenvalue of 2 is coming from the factor of lambda minus 2, and so 2 has algebraic multiplicity 1. And so in a sense, we could list the eigenvalues of the matrix A as -1, -1, and 2. Now, what makes it work in this case is that the geometric multiplicities of the eigenvalues are equal to the algebraic multiplicities of the eigenvalues. So when we look at the eigenspace associated with -1, it has dimension 2. So the geometric multiplicity and the algebraic multiplicity agree. Again, when we look at the eigenspace associated with lambda equals 2, we find that it has dimension 1, so its geometric multiplicity is equal to its algebraic multiplicity. So anytime we have the geometric multiplicities coinciding with the algebraic multiplicities, we will find that the matrix in question is in fact diagonalizable. We will always be able to find the sufficient number of linearly independent eigenvectors to demonstrate that the matrix is in fact diagonalizable. Now here's the diagonal representation of the matrix A. On the right here we can see the product of P, D, and P inverse. The matrix P, of course, consists of the 3 eigenvectors of the matrix A, and the matrix D consists of the corresponding eigenvalues of the matrix A. Now, guided by this last problem, we are now ready to discuss the diagonalization theorem, theorem 4.27. Let A be an n by n matrix whose distinct eigenvalues are lambda 1 through lambda k. The following statements are equivalent. Statement A is diagonalizable. Statement B, the union script B of the bases of the eigenspaces of A contains n vectors. And statement C, the algebraic multiplicity of each eigenvalue equals its geometric multiplicity. Now let's make sure we understand how theorem 4.27 was operative in our previous example. In that example, the matrix A was a 3 by 3 matrix with 2 distinct eigenvalues, -1 and 2. Now, when we looked at the eigenspaces of the 2 eigenvalues, we saw that the eigenspace corresponding to -1 had dimension 2, and the eigenspace corresponding to the eigenvalue of 2 had dimension 1. When we merged those bases together, we found that the matrix A had 3 linearly independent eigenvectors, and that is enough to show that the matrix is diagonalizable. We also saw that the algebraic multiplicity of each eigenvalue was equal to its geometric multiplicity, and that is equivalent to saying that the matrix A has 3 linearly independent eigenvectors. Now let's use the diagonalization theorem to show that a matrix is not diagonalizable. So let A be the 2 by 2 matrix that you see here. Let's show that A is not diagonalizable. Now we begin our analysis, as always, by computing the characteristic polynomial of A. And in this case, it's very easy to see that the characteristic polynomial of A is lambda minus 3 squared. Now this shows us two things. First, A has only one eigenvalue, namely lambda equals 3, and this lone eigenvalue has algebraic multiplicity of 2. On the other hand, when we look at the eigenspace associated with this eigenvalue, we find that it's spanned by a single vector. In other words, the geometric multiplicity of this eigenvalue is equal to 1. Now, according to theorem 4.27, the game is over. This matrix A is not diagonalizable. The geometric multiplicity is coming up short of the algebraic multiplicity, and that means that the matrix A is not diagonalizable. Now I want to close by working a problem with you that shows the power of this diagonalization method. The matrix A, this 2 by 2 matrix, has eigenvalues lambda equals 2 and lambda equals 1 with corresponding eigenvectors 3, 1 and 2, 1. So step 1, find a diagonalization of the matrix A. Step 2, express A to the 5th, and in doing this, we're going to use the diagonalization to help us find a simple way to express A to the power of 5. And then in part 3, we want to find the limit of 2 to the minus n times the matrix A to the power of n as n goes to infinity. So join me at the document camera for the solution to this problem. All right, welcome to the document camera. In this problem, we've been given a matrix A, and we've been told that this matrix A has 2 eigenvectors corresponding to the eigenvalues lambda equals 2 and lambda equals 1. In step 1 of this problem, we're asked to find a diagonalization of the matrix A. And we know the recipe. The diagonalization theorem 4.23 tells us that the first thing to do is to form a matrix P whose columns are these independent eigenvectors. And so I'm going to identify the matrix P as the matrix with columns 3, 1 and 2, 1. Next, we form a diagonal matrix consisting of the corresponding eigenvalues. So we'll have a matrix D, and it's going to have as its diagonal entries 2 and 1. And then finally, the last element in the recipe is the inverse of the matrix P. Now in this case, that inverse matrix is easy to express because the determinant of our 2 by 2 matrix is 1. And so I can simply swap the diagonal elements and change the signs on the off diagonal elements. Okay, so our diagonalization of A, our representation of A, is going to be A, which has entries 4, -6, 1, and -1, can be represented as the product of these 3 matrices: P, D, the diagonal matrix, and P inverse. And so there's our diagonalization of the matrix A. It's A equals P times D times P inverse. All right. Now, let's put this to work. In part 2 of this problem, we're supposed to compute A to the power of 5. Now that actually would be simple enough to do. I could simply take this matrix A, I could find the square of A, and then I could square the square of A to get me to A to the 4th, and then I could take A to the 4th times A to get to A to the 5th. That's not too difficult, but what I want to show you is a deeper underlying principle. When I want to compute a power of a matrix, it's very convenient to do this if you have a diagonalization of that matrix. So let's say you already have your matrix in diagonal form. Let me show you how powers of this matrix can be simply expressed in terms of this diagonalization. So, for example, if I wanted to simply compute A squared, we could think of that as P times D times P inverse times P times D times P inverse. Now, by reassociation, I could write this as P times D times P inverse times P times D times P inverse. So I could imagine multiplying these two inner matrices first. But P inverse times P is simply the identity matrix. The identity matrix times D is just D. And so what I'll end up with here is P, D squared, and P inverse. In other words, what we're going to find is that anytime I take a power of the matrix A, let's say A to the power of 2, that's going to be equivalent to taking D to the power of 2 and then sandwiching it between P and P inverse. All right, so the general principle is this. The nth power of the matrix A can always be expressed as P times the nth power of the matrix D times P inverse. Now, what makes this particularly simple is that the power of a diagonal matrix is always going to be it's always going to be a diagonal matrix where that power gets placed on each of the diagonal entries. Now let's look at this for D squared, and you'll be able to see why this will be true in general. So if I take the matrix D times itself, we can clearly see what's going to happen. When I do this first dot product, I'm going to get 2 squared plus 0. Then I'll have 2 times 0, which is 0, 0 times 1, which is 0. So I'll just simply get a 0 here. We'll have a 0 plus 0. And then finally we'll have a 0 plus 1 squared. Okay? And that pattern is going to persist. D to the power of n is simply going to be the diagonal matrix with entries 2 to the n and 1 to the n. Okay? So what this tells me is that if I want to write a power of a to the n, we're simply going to have the matrix P the matrix D to the n, and the matrix P inverse. And so that ends up being a very convenient way to write the power of the matrix A to the n, right? I want to write A to the n, and I can simply express it through the diagonalization as P times D to the n times P inverse. Now, what does this mean in particular for A to the power of 5? So A to the power of 5 is going to be the matrix we get by taking 3, 2, 1, 1 times the matrix consisting of 2 to the 5th, which is 32, 0, 0, 1, times the matrix 1, negative 2, negative 1, 3. And when you work out this matrix product, you end up with the 2 by 2 matrix consisting of 94, negative 186, 31, and negative 61. And quite honestly, if our goal was to simply compute A to the 5th, this is actually not that much faster than just working with the original matrix and computing its 5th power, as we talked about earlier. So we could get to this result without the diagonalization. But let me try to sell this to you with the next part of this problem. And this is often the thing we're interested in. We want to know something about the behavior of the matrix A to the n as n goes to infinity. And so in this last part, we're being asked to figure out what happens when I take the matrix A to the n and I scale it by 1 over 2 to the n. Okay? this scalar in front is going to 0 very, very quickly, right? This is going to be 1/2, then 1/4, then an 1/8, then a 16th, etc. So this scalar in front is going to 0. At the same time, this matrix a to the n is exploding. Its entries are getting bigger and bigger. And so the question is, what happens when I scale the matrix a to the n by 1/2 to the n? What happens to that as n goes to infinity? Now, one way to think about this is we're computing 1/2 to the n times p times d to the n times p inverse. And one of the properties of matrix multiplication vis-a-vis scaling is that I can take that scalar and I can imagine applying it to the matrix P, or to the matrix D to the n, or to the matrix P inverse. I can scale the entries of any one of these three matrices by that scalar. And in this case, it makes sense to think of scaling the matrix D to the n by the scalar 1/2 to the n, because that's simply going to divide all of the entries of D to the n by the scalar 1/2 to the n, or it'll divide them by 2 to the n. So if we think about taking the 1/2 to the n and scaling the matrix D to the n by it, we can see that this representation is going to give us the matrix P times the matrix that's obtained by scaling everything inside D to the n by 2 to the n, or multiplying by 1/2 to the n. So I'll get a 1 here, a 0, a 0, and here I'll have a 1/2 to the n. Then I've got P inverse. Okay, now the question is, what happens to this as n goes to infinity? Well, we can see that n is appearing only here, 1/2 to the n. And as n goes to infinity, this entry is going to converge to 0. And so this is going to converge to the product that I get. So this is as n goes to infinity. This will converge to the product of 3, 2, 1, 1 times the matrix 1, 0, 0, 0 times the matrix 1, -2, -1, and 3. And when you work out this product, you get the matrix 3, -6, 1, and -2. And so we can think of this matrix as the limit of 1/2 to the n times a to the n as n goes to infinity. And so through this diagonalization method, we're able to kind of figure out what happens as n goes to infinity in this scalar 1/2 to the n times a to the n. All right, that's all I wanted to show you from section 4.4. And with that, I would like to bring a close to this section.